Let us start with the stiffness method of analysis of plane-framed structure. We have completed the analysis of this plane-frame structure like beams, trusses and rigid plane frames by flexibility method. Now we will take up the stiffness method of analysis. The procedure to be followed is similar to flexibility method. So here also the method of analysis we have to adopt what is known as this transformation matrix approach. Transformation matrix approach. In this, we are going to find a relationship between the force and displacements in two coordinate system, one local coordinate system and another global coordinate system. We derive the relationship between the global and local coordinate systems using what is known as principle of contra-radiance. This you have already seen how this principle of contra-radiance can be applied to flexibility problem. The same thing now we will apply for the stiffness method of analysis, the principle of contra-radiance. So the principle actually, so the displacement vector defined with respect to the displacement vector defined with respect to element coordinate system, can be transformed to system or global coordinate system. Df. The same displacement vector which has been defined with respect to coordinate local or element coordinate system. It can be transformed into system or global coordinate system through a relationship defined by dm is equal to dm, vector dm. It is related to global displacement system by a matrix called a displacement transformation matrix. It is defined by this relationship where R is called displacement, where R is called displacement transformation matrix. Displacement transformation matrix is relationship between this local coordinate displacement vector and global coordinate system vector. It is they are related through a matrix called for displacement transformation matrix, because this is transformation matrix approach we are doing. So we have to transform whatever the equations which we derive for the local coordinate system to global coordinate system like this. So by principle of contra-radiance, which I am just using now, by principle of contra-gradients, This relationship gives PS. Here displacements are related. Now, by principle of contract-radius, its corresponding forces are going to be related by this equation. Okay, then by principle of contract-radius, PS is given by RT into PM. So this is the particular thing. When displacement dm local is related to displacement vector in the global by this transformation matrix, then by principle of contract-radius, the forces, the global force, it is actually converse of this, the global forces are related to local forces by transpose of that same displacement matrix. So this particular thing, which we call it as the principle of contract-radius, it can be derived by the work done. Actually, the work done by these two system principles, one local coordinate system, we have dm and pm. Global coordinate system, the corresponding displacement and forces are dx and ps. So the work done by this global force and global distance and work done by local force and local displacement, so they should be equal. Whatever may be the system of force and displacement we define, the total work done has to be same. The total external work done due to global system, it is going to be stored in the structure by development of the internal member forces and the corresponding displacements, and thereby internal work done, internally work is done, and this external work done will be equal to internal work done. So this equation 2 can be established. Equation 2 that is the principle of contract-radius, can be established by work done. By equating the work done by external force PS, by external force PS resulting in displacement dx, by equating the external work done by external force PS resulting in displacement dx to internal work done or energy, internal work done or energy by internal member force system, internal member force PM, that is the external work done, that is dst into PM is equal to dst into ps is equal to dm into PM. This is external work done, this is internal work done, they should be equal. Why we are using for ds transpose means both these dx and ps, they are of same order. When we are multiplying the two matrices of same order, one should be transpose of the other, then only multiplication is possible. That's why we are writing dst ps is equal to dm pm. This you have already seen in flexibility method also. This you can call it as third equation. Now, by transposing equation 1 on both sides, we get DMT is equal to RT into DST. Now, we call this as 4. Now, substitute this in this equation. DMT, you substitute in 3. So, from 3 and 4, we get DST PS is equal to, for DMT, I will substitute this RT DST into M. I am substituting for DMT value of RT DST here like this. So now you can compare this equation 5 and then from equation 5. So this DST get cancels. You have PS is equal to RT PM. This is what I am going to get. So this is nothing but, I don't know, that's fine, just leave it as it is. This is nothing but this equation 2, same as equation 2. That's what I have told. So this equation 2 can be established. So you can derive this by just using this work done principle. That is, external work done has to be equal to the internal work done. Using that principle, I can just establish this relationship. So this is known as principle of contragradient. Here, if you determine this relationship between local coordinate displacement and the global coordinate displacement through a displacement transformation matrix, then the corresponding forces you can relate it by this transpose using this principle of contragradients. So this particular principle is being used in the derivation of the stiffness matrix member or element stiffness matrix to global stiffness matrix. Now, we have the relationship between the force and displacement. So, using the force displacement relationship in two coordinate systems, namely from global. So the relationship between force and displacement are PS is equal to Ks into ds, and from element coordinate system, the force and displacement relationship, you can take it as Pm, Km into dm. So using this force displacement relationship, which has been defined in global coordinate system and local coordinate system from these two equations, in this 2 into we get. Now I have established this equation 2 by principle of contragradients I have derived here. So in this principle, if I use this force displacement relationship, so we get, instead of PS, I can write Km, PS I can write Ks into ds. PS is nothing but PS is equal to Ks ds, R equals RT into PM. PM is nothing but Km into dm. This is what I am going to get. So now again I will substitute this dm is equal to R ds from 1 using 1 we get Ks into ds is equal to RT into Km. dm is from 1 is nothing but r into dx. So this dx get cancels. Now you got the relationship of this Ks is nothing but RT into Km or. So this is the important relationship which relates the element stiffness matrix Km with the global stiffness matrix Ks. So that particular equation we are using in the stiffness method of analysis. Already I have derived the element stiffness matrix, that is Km, for all the elements of truss structure, rigid plane frame structure as well as beam structure. Now we can convert that into global stiffness matrix by this force transformation matrix approach. So for that we have to define what is meant by this force displacement transformation matrix, and using the principle of contamination we have arrived at these two relationships, one A, another B, and using this principle we are doing the analysis by this stiffness method. All the problems we can just analyze using this. This is the theory behind this stiffness method of analysis. This you have to remember. The same thing, of course there is nothing new here. The same thing I developed even in flexibility method also. Same principle of contrariety, but there I use the force displacement transformation of matrix. That is, I use Pm is equal to T into Ps, and I developed the similar type of equation, that flexibility matrix relationship I developed there, and that I completely have used in the analysis of beam stresses and strains, which you have already seen. Now I am deriving the similar type of the relationships by using what is known as force displacement transformation matrix, using the same principle of contrariety. So I have derived that, and this principle we are using in the stiffness method of analysis. So this much theory you have to remember, and of course in addition to this particular theory, already you have to remember the element stiffness matrix. So that also I have derived, that also you have to remember. The element stiffness matrix which we have developed. So for truss member, element stiffness matrix is given by AE by L into 1 minus 1 minus 1 1. This is the for truss or for elements subjected to axial force only. Like that, I have derived an expression for this is like this. Only when it is subjected to axial force, the truss element 1, 2 subjected to an axial force like this, and length of the element being L and axial rigidity AE. It is given by this, that is called element stiffness matrix. And similarly for beam element which is having a length L and flexural rigidity EI and subjected to the two end displacements, that is theta 1, theta 2, and with end moments M1 and M2. So the relationship between this M1 and M2 with theta 1, theta 2, that is nothing but stiffness matrix, and that is given by 2EL by L, 2, 1, 1, 2, and theta 1, theta 2. So this is for beam elements and rigid frame elements, which are actually rigid elements. Beam elements and rigid frame elements, which are actually rigid. So you have to remember this, that is, this is called stiffness matrix Km. So knowing this Km for this beam and rigid frame elements as well as this actually loaded elements, that is Km, you can develop Ks from this principle. Then you can just write the relationship between force and displacement or in the global coordinate system, that is Ps is equal to Ks ds. Then you can solve this either by Gaussian elimination, Gauss-Jordan method, or whatever it is, or by inversion of matrix, you can evaluate your known displacements. So because analysis involves determination of displacements due to the given loadings, as well as you have to find the internal member forces. So the displacements due to the given load, after determining Ks, you can determine using this relationship, and then the internal member forces straight away you can determine from that relationship between the internal member forces and the displacement. Again, this displacement dm, you can convert it into, from the global, you can convert that into dm from that relationship of force displacement transformation. Then you can evaluate the combined internal member forces. Thereby, you can complete the analysis, that is the internal member forces as well as the displacement you can evaluate. So that is the procedure we follow during analysis. This much theory you have to remember, and now we will take up straight away the problems, that is analysis of beams, analysis of trusses, as well as analysis of rigid frame one by one, using these principles. So the steps to be followed, already I told, it is similar to flexibility method. The 7 steps which I just used in flexibility method, same 7 steps you can adopt here. Now straight away I will take up an example, that is analysis of beams by this stiffness method. So now I will take up an example straight away. Analyze the beam shown in figure. So a continuous beam, I will take it. So the beam ABC, continuous beam ABC, which is fixed at end A and supported at B and C by knife supports. So it is subjected to a uniformly distributed load of 50 kilonewton per meter on span AB and a concentrated load, central concentrated load of 80 kilonewtons on span BC. In this fashion. And of course, there will be the overhang also in this beam. So this is the problem which we worked even in flexibility method, and same problem I have taken here by this stiffness method. So let us analyze this beam by stiffness method now. Already the same problem I have analyzed by flexibility method. You can just refer to your earlier board, and now you will derive and we will analyze the same deal by this stiffness method procedure which just now I explained. So the first step is element coordinates. Element coordinates. So it is similar to flexibility method. We have to define a set of element coordinates. Element coordinates means they indicate the positive direction of the internal forces which we have to determine at the ends of the members. The element coordinates are nothing but the direction of the internal member forces which we have to evaluate during analysis. So, these internal member forces, we select always the moments as equal to the moments at the ends. So, in this member AB, the moments at the two ends whose direction in clockwise is taken as positive. So, this is called coordinate 1, this is element coordinate 2, this is for BC member, similar to AB, there are two coordinates, that is the moments at the ends in the clockwise direction only as positive. So this we call it as element coordinates because analysis means determination of internal member forces developed due to the given loading as well as the displacements. So that is what we are supposed to evaluate during analysis. Now here in the first step we will identify what are the internal forces which we have to determine during analysis, that we can get the element coordinates, and these are the forces. So this given problem is that whenever overhang is also given, that overhang you can just remove it for the analysis purpose, and whatever the moment which is going to be created from that overhang portion, it is taken as the joint load like this. Here, the same problem I can make it as equivalent to this particular thing. I have removed the overhang portion, and because of this overhang, there is a moment that created due to external load at the joint C, and that moment will be 10 into 2, 20, and that 20 I am going to consider acting at the joint C. So this particular problem we can analyze taking that overhang moment acting at the joint in this fashion. Normally, whenever overhang is given, that overhang is replaced by equivalent joint moment at the immediate main joint of the structure. Similarly, if the overhang is given on the other side, there also you can replace it by equivalent joint load and do the analysis. So that particular joint load is I have taken. That's why here I will take only joints A, B and C. So this is the element coordinates, and we have to find out the forces, that is element forces, which we call it as PM vector, that is PM will be equal to PM1, PM2, PM3, PM4, PM5, PM4. There are 4 member forces corresponding to these coordinates. It's a 4x1 matrix. This we have to determine. And then we have to assume each of these members to be fixed at the joints, at the ends, like this. Member AB is assumed to be fixed at A and B. Likewise, member BC is also assumed to be fixed at B and C, and due to whatever loading is there, generally member loading, during the analysis, we just convert that member loading into equivalent joint load by determining the fixed end moments at the end. So these fixed end moments, due to be here, we have Two member loading 150 UDL 50 kilonewton per meter, another 80 kilonewtons acting on members A, B and BC. So we assume the member A, B and BC to be fixed, and due to that fixity, we find what is the fixed end moment develops, and those fixed end moments corresponding to these element coordinates that we take as for the analysis purpose as the external load. Instead of the member load acting on the structure, we convert that member load into equivalent joint loads result. And this equivalent joint moment will be WL squared by 12, and that is, the span is 6 meters, that is 50 into 6 squared by 12, that is equal to 150. Here also it is 150. Here it is WL by 8 because it is concentrated load. WL is 4 meters, WL by 8, that is 40. Here also it is 40. This is minus WL by 8, this is plus WL by 8 because the element coordinate positive direction I have taken clockwise positive, but here fixed end moment will be, here it is anti-clockwise because applied moment will be clockwise, resisting will be anti-clockwise. Here applied will be anti-clockwise, resisting will be clockwise. So likewise here also. So that this moment I will take it as minus, this as plus, this as minus, this as plus. So that particular thing we call it as the fixed end moment, and we indicate it by matrix PMF. PMF corresponding to this, because loading acting on the external load will be replaced by equivalent joint load, and that will be equal to, here it is corresponding to 1, it is minus 150, corresponding to 2, it is plus 150, corresponding to 3, it is minus 40, corresponding to 4, it is plus 40. This is the fixed moment corresponding to these element coordinates. So this much information you have to calculate or gather in the first step. First step, you have to identify the member and forces which you have to determine during analysis, that is by coordinates. That is, we call those coordinates as 1, 2, 3, 4 with star. So this is the element coordinates. And you have to determine what are the internal forces to be determined corresponding to these element coordinates, that is these. Ultimately at the end we have to determine these forces, and to determine these forces first, whatever the external load which is there, that I have to replace it corresponding to these end element coordinate loads by finding their fixed end actions in this fashion. This you already know, the fixed end moment standard that you have to replace it. That's the first step for element coordinates. Then the second step is the system coordinates. Which consists of evaluating what is known as kinematic indeterminacy, the coordinates corresponding to the kinematic indeterminacy of the structure. So in the flexibility method, you are identifying the static indeterminacy, and the coordinates corresponding to those static indeterminacy, you are calling it as system coordinates. Here, the kinematic indeterminacy is equal to this already you know. How to determine the kinematic indeterminacy, which is nothing but the number of unknown joint displacement, and the kinematic indeterminacy I gave you a formula which is nothing but for beam structure, it is 3j minus 3j minus or J. J is the number of joints, R is the number of support reactions. Here, number of joints is 3, so that is 3 into 3 minus R is number of support reactions, that is 3 here at fixed end, and 2 at roller support. So 3 plus 2, it is 5. So here it is 3 plus 3, this is 3j minus r. That is 3 into 3. My number of joints is 3. 3 into 3, 9. Minus r is 5. So it is 4. Kinematic indeterminacy is equal to 3j minus r. That is 4. We are getting, not here 3. It is 2. 3 into this j. Number of joints, correct, 3 into 3 minus or unknown support reactance 5, 9 minus 5 is equal to 2. Number of joints, of course, it is 3, 3, 9. Support reactions 5. And of course here, as it is, you can see that each of these, suppose if you take each of these particular problems here, at each joint you have possibly 3 displacements possible at each joint. Here, since it is fixed, no displacement is taking place because at fixed end, no displacement. And here it is roller, so vertical displacement is not possible. Horizontal displacement, it is possible. But here, at this end, for the member AB, horizontal displacement, if at all it is possible here also they should move. Because this member is assumed to be accelerated. So if this moves, this also should move, but this cannot move because of fixity. So this also cannot move. The condition we are applying. So this is also 0, and here likewise same argument. This is also 0. So and this vertical is also 0. Only these 2 rotations which are possible. That's why this kinematic indeterminacy is 2, not that 4. So kinematic indeterminacy is 2, and there are the rotations at B and C. That's the only possible displacement. So that you indicate it by coordinates, like this. The possible displacements are along 1 and 2. Here it is displacement along 1, D1. Here displacement along 2. That is the system coordinates corresponding to the kinematic indeterminacy. That's the second step. So here I have to evaluate these 2 displacements corresponding to these system coordinates D1 and D2. So during analysis, now I have to determine these unknown internal member forces corresponding to element coordinates and unknown displacements corresponding to these 2 coordinates, because here there cannot be any displacement. Here vertical displacement is not possible at all, and horizontal displacement, because we assume each member to be accelerated, though it is possible here horizontal displacement, because the other end also, if this moves, this also should move. If this cannot move, so this also cannot move. So the horizontal displacements are not there at these 2 ends. So ultimately we are left with only the possible 2 displacements. And corresponding to these displacements, corresponding to these coordinates, we have to evaluate during analysis that I have defined. So this is our second step. In the first 2 steps, we are just identifying what are the things which we have to determine during analysis. One is internal member forces corresponding to these member coordinates. Another, the displacements corresponding to these global or system coordinates. And now we can determine this load in the global element because this is system coordinate. This is with respect to system coordinate only. We are evaluating the displacements and corresponding to that, whatever load which is there, that we have to calculate. And this load is nothing but the joint load given corresponding to these coordinates minus PA due to equivalent member fixed action. Whatever load which is there corresponding to these coordinates, that I have to subtract from the joint load. So that already I have calculated here. So PJ external joint load, it is given only here at this joint. There is an external joint load due to overhang. Here we are using the overhang moment, so that we have to take. So now here along coordinate 1, the equivalent joint load will be, that is at the joint B. This is joint C, this is a joint A. At joint B, corresponding to the member AB, the load is plus 150. That's what I have taken here. It is plus 150. And corresponding to, from this member BC, corresponding to this same coordinate 1, the load is minus 40. It is anti-clockwise direction. So at the joint B, from the member AB loading, we have a load of plus 150, and from the member BC at the joint B, we have a load of minus 40. So the net load will be 150 minus 40, so it will be 110. That is PMS. PMS is this. Correct? 150 minus 40, that is the load corresponding to this coordinate 1 from BA and BC. From BA it is plus 150, from BC it is minus 40, 150 minus 40, it will be 110, that is the PMF. So PJ, there is no external joint load, so that will be 0 minus 110. PMF is 110, joint load is 0. That is corresponding to coordinate 1. Then corresponding to coordinate 2, that is at the joint C, only this load, that is plus 40, that is the member load. PMF is plus 40, but PJ is also there because this problem has a overhang. Because of that overhang, external joint load is coming. So PJ will be the 20 and PMF is plus 40, it is minus PMF, so it is 20 minus 40, that is the load corresponding to 2. So PJ minus PMF, whatever external joint load is there, minus the equivalent member load acting at the joint, which I have calculated. So this PS is nothing but your 110 and minus 20, both are minus. 20 minus 40 minus 20 is minus 110. This much calculation you have to do in this second step. You have to identify element coordinates, you have to identify system coordinates. Then the third step is unassembled stiffness matrix, similar to unassembled flexibility matrix. So here you have to determine what is known as unassembled stiffness matrix. That is third step. I told you the same step for 7 steps, whatever I have defined in flexibility method of analysis, you have to do here also. So already I have defined the stiffness matrix of each element. Here it is beam problem. So for each beam problem, beam element, already in the previous step, I told the stiffness matrix for a beam member, that is if you take AB member or the AB member, stiffness matrix is given by L by 2EI to 1, 1, 2. This is what this stiffness matrix, which I just told previously, so I have to use it. So the stiffness matrix or element stiffness matrix of the member AB is treating the moments at the ends as the unknown force, independent force. So that is the stiffness matrix you are going to get. And here, L is the length is 6 meters. Here is fractional rigidity, that is 2EI. So this will be 2 into 2EI. And of course, this is 2, 1, 1, 2. So this is nothing but 3 by 2 into 2, 1, 1, 2. This is the stiffness matrix of member AB. Then the stiffness matrix of member BC. That is the BC. That is nothing but, again, same formula, L by 2EI, 2, 1, 1, 2. Here, L for BC, it is length 4 meters, divided by 2EI. EI value is EI itself, whereas here it is 2EI, here it is just EI, then it is 2, 1, 1, 2. Or this is nothing but 2 by EI, 2, 1, 1, 2. This is element stiffness matrix. So therefore, on a sample stiffness matrix, AM, it is nothing but a assemblage of all the member element stiffness matrix. We have to place it along the diagonal of the matrix. So here I will take EI 1 over, this is 3 by 2 EI. So I will take 1 by EI outside. If I take 1 by EI outside, then here this I have to multiply by 6 into 2, 12, or 1 over 2, okay, 2 by EI if I take outside, 6 into 12. So here it is 12 because I have taken 1 over EI outside. So this I have to multiply by 2 by 3. So that is 2 by 3 means it is 4. So this 1 over EI what I have taken outside, this 3 by 2 I have to take it inside. So that 1 over EI I have taken means this 3 into 2 I have to take it inside, and that I have to divide it. I will get 1 over EI into this. I will calculate and show you. This will be 2 into 3 divided by 2 into 2. 2 into 3 divided by 2, that is just 3. You are getting 3, and then this will be 3 into 1 by 2, that is 1.5. 1.5 means to make it easy, I will take this, here LCM is 2EI. I will take 1 over 2EI outside, that is easy. 1 over 2EI if I take it outside, then this has to be multiplied by 3 inside, 6, then it is 3, then here it is 3, here it is 6. Because 6 by 2 is 3, that 3 inside, this is same as 3 by 2. 3 by 2, huh? I'm taking 1 over 2 outside. So then this will be 6, 3, 3, 6. And here 0, 0, 0, 0. Then here 1 over 2 I have taken outside. So this will be 8, then 4, 4, 8. So these two are 0. So this is the matrix corresponding to element 2. This is the matrix corresponding to element 1 that I am arranging along the leading diagonal. This is called unassembled stiffness matrix. Right? So now you see whether it is same as this. So this 1 over 2 EI 6, 3, 3, 6. So if I take 3 outside, I will get 3 by 2 EI 2, 1, and 2. It is same as this. Similarly, this matrix is 1 over 2 EI. This will be 8, 4, 4, 8. If I take 4 outside, I will get 1 over 4 by 2 EI means it is 2 by EI. This will be 2, 1, 1, 2. It is same as this. So this particular thing, whatever I have, that is okay. This is my unassembled stiffness matrix. It is 4 by 4. That is the third step. Then fourth step. We have to determine what is known as the displacement transformation matrix. The fourth step. Displacement transformation matrix. That is, which we call it as R. So to obtain this R, is just I define this R as nothing but the matrix which relates the local coordinate to global coordinate. I explained by defining principle of contrariety. This is what the displacement transformation matrix R I define. So the elements of R we are going to get by applying unit load along the system coordinate, one at a time. That is, or successively along each of the system coordinates, I have to apply a unit load and find the corresponding displacement along the element coordinates. That is how you generate this transformation matrix. So that means I have to take this structure and like this is the structure given. First I have to apply a unit displacement along the global direction 1. So like this is the global direction 1. I have to give a rotation at B in that fashion. If I give a rotation like that, it will move like this in this fashion. And I will keep all other displacements fixed when we have to give displacement only along 1. That is along 1. I am giving a unit displacement like this. D1 is equal to 1. I will give D1 equals 1 in that fashion, keeping all other coordinates fixed. So D2 will fix, other transform will fix only along D1. I will give displacement equal to unity. Because by fixing all others, since we are fixing all others, we get and calculate what is the displacement corresponding to each of these element coordinates. So here, since I am fixing all of the coordinates, the displacement corresponding to this element coordinate, that will be 0. Displacement corresponding to this 2, it is 1 plus 1 in the same direction clockwise, and displacement corresponds to 3, it is again 1 here, that is clockwise positive. Displacement along 4, it is 0 because here we don't allow any displacement. So I will get the first column of this 4 displacement transformation matrix. I told the columns of this matrix, it is a displacement transformation matrix, you can determine by applying unit displacement along each of the system coordinates one at a time and find the corresponding displacements at all other coordinates. So when you give unit displacement along one coordinate, all other displacements you have to keep it 0. That's also another thing you have to remember. So here along element coordinate 1 displacement is 0, along element coordinate 2 displacement is +1, 3 it is +1, 4 it is 0. That is the first column of the force displacement transformation matrix. Then you have to apply the same displacement along the coordinate 2, along global coordinate 2 like this. So that means we have to apply a unit displacement in this direction, keeping all others 0, and apply a unit displacement here this, here A, G. We have to keep it fixed. So I have to calculate what is the displacement now due to the along these element coordinates. So I am applying d2 equals 1, all this will be 0. That is the second column of this R. So if I apply this here, here it is 0, here it is 0, here it is 0, here it is 1. That means the second column it will be this 3 0 1. Therefore, you got R, this displacement transformation matrix, it will be 0 1 1 0 0 0 1. It is a 4/2 matrix. This is what we have to do in the fourth step. Fourth step, I have to determine this displacement transformation matrix by giving unit displacement along global system coordinate system successively, one at a time, and calculate the displacements corresponding to that all at all element coordinates. So that will give you the columns or each columns of that displacement transformation matrix. So third step is calculation of decimal stiffness matrix. Remembering the standard element stiffness matrix. For each element you have to calculate stiffness matrix and place them along the leading diagonal to get the assembled stiffness matrix, and then to get the displacement transformation matrix you should go on applying the displacement of unity along each of the global coordinate system successively and calculate the corresponding element displacement as have done. That will be workforce transformation matrix. So if you do this much exercise, then next step you have to apply that formula whatever I have derived just now and calculate the structure stiffness matrix. That is fifth step. You have to calculate structure stiffness matrix KS. So just now using that principle of contra gradient, I derived the formula KS is given by RT into KM into R. That's what I have derived in the previous steps. So that formula I have to use and you have to calculate this structure stiffness matrix. It's only matrix operations, nothing other than that. Remember the theory, basic principles which I explained, then perform matrix operation of addition, subtraction, multiplication, whatever it is, you by matrix algebra and compute the corresponding values. With that, you can find out the internal forces developed and the displacement. That is the analysis procedure. Now, first step, I have to work out this Ks. The Ks is nothing but or the transpose of R matrix. R matrix just now has generated. Transpose of this matrix means I have to change the column to rows. That is, that R matrix I have to write it in this direction. This is nothing but RT. That columns I change it to row. This is RT. Km I have generated here, that is for the structure, for the unassembled matrix for the entire structure I have assembled, so that is nothing but 1 over 2 EI 6336, then it is 8 4 4 8. That is Km into R. R is this. Okay. To take this 0 1 1 0 3 0 1. This is RT Km R. So this multiplication of this matrix I do follow. Now this is 4 by 4 matrix. This is 4 by 2 matrix. So column here is equal to row here. Multiplication is possible. So if you multiply this, you will get a 4 by 2 matrix. The resulting matrix will be a 4 by 2 matrix. This column and row get cancelled, we get the net matrix as 4 2. So that is, of course, this 1 over 2 EI, you can retain as it is. So each of these first row you multiply by the first column, then second column, write it here. So here 6 into 0, 0, 3 into 1, 3, 0, 0. So it is just 3. Next second column, 6 into 0, 3 into 0, 0, 0, 0. So it is 0. Next second column, 3 into 0, 6 into 1, 6, 0, it is 6. Then 3 into 0, 6, 0, 0, 0, it is 0. Next third column, 0, 0, 8, it is 8. Then 0, 0, 0, 4. Next last, 0, 0, 4. Another side. Then this, it is 0, 0, 0, 8. So that is a 4 by 2 matrix. Multiplication of these two matrices. That is Km into R. So this I have to multiply by this R. 1, 0, 0, 1. So this is R into this KMR. So this is a 2 by 4 matrix. 2 rows, 4 columns. So here, column is 4, row 4, they are equal. So if I multiply this, so resulting matrix will be a 2 by 2 matrix. So that is my KS matrix. So this is equal to 1 over 2 EI, I will keep it as it is. 1 over 2 EI, here same thing. First row, I will multiply by first column, then first row, second column. I will write it here, here. So that is 0 into this, 1 into 6, 1 into 8. 1 into 6 plus 1 into 8, that is 6 plus 8, 14. This is 0, so that is 14. Next, second column, 1, 0, 1, 0, 1 into 4, 4, 0, 4. Next, second column, 0, 0, 0, 1 into 4, 4. Then second column, 0, 0, 0, 1 into 8, 8. So that is the 2 by 2 matrix. So my way, always this structure flexibility matrix is symmetric matrix. So it is a symmetric. matrix. So that is your fifth step. You have to develop structure, stiffness, matrix. After developing structure, stiffness, matrix, so you have to find the inverse of the stiffness matrix, or you can do the equation solution by Gaussian elimination, whatever it is. Here I go for inversion of this. So you find out Ks inverse, that is inversion of this, that is nothing but 1 over 2ei will become 2ei by 1, 2ei by 1, so that is determinant of this is 14 into 8, that is 112 minus 16, that is the determinant of this, so that is 96 into cofactors of this, cofactor of this is 8, then minus cofactor of this, it is minus 4, and this is minus 4, this is 14. So that is what inverse of this matrix. Or here I can take 2 outside, so I get 4 divided by 96. So if I take 2 outside, I get here 4 minus 2, 7. Or this is equal to ei by 48 to 4 minus 2 minus 2, 7. That is the inverse of this matrix. So next, sixth step. So you have to find ds. So calculations are only up to fifth step. Then final 2 steps or evaluation of these unknowns. Unknowns, what is that? You have to determine during analysis that I have defined here. One, you have to find out PM, the end moments, PM1, PM2, PM3, PM4. You have to determine. Next, in the second step, you have to determine these unknown displacements. Unknown displacement, unknown internal forces. This you have to compute in the last 2 steps. So here, sixth step, I will recommend is to find ds, or that is, you see the number ds. ds is equal to d1 dt. That I have got it. So for this, we have the force displacement relationship. ps is equal to ks into ds. That I have already told using the principle of contrariety. I told relationship between system coordinate and element coordinate is given by ps equals ks ps, element coordinate is pm equals km dm. So that one I will use. Here ps already have determined ps here. ps have determined. So that is minus 110 and minus 20. That is ps therefore is equal to ks. ks is nothing but I have generated 1 over 2ei into 14, 4, 4, 8. Or if I take 2 outside, I will get here 1 over ei. Here I will get 7, 2, 2, 4. If I take 2 outside, here 7, 2, 2, 4. And that 2 and these 2 get cancelled and left with 1 over here. So this is ks into ds. That is what we have to do today. ds is nothing but d1, d2, which I have to determine. In second step, I have told what is that we have to determine. One is this ds, another pm I have to calculate by performing all other operations using that principle of contrariety and other. So now you multiply this. Therefore, d1, d2 is nothing but, that is ds. Therefore, ds equals d1, d2 is nothing but as inverse ds. This divided by 1 over, divide the 1 over ks means it is ks inverse. So that is nothing but inverse of this. Either you can solve this equation by Cauchy elimination, or this you can get d1, d2, or by inversion of patterns. You can get it. Straight away look for inversion. So that inversion is given by ei by 48 4 minus 2 7 into PS is minus 110 and minus 20. So if you multiply these two, you will get d1 and d2. I will have the value of d1, d2, straight away I will write it. So d1 so the d1, d2, therefore d1, d2 is given by 1 over ei is this okay? Oh, that by doing the inverse, this to be taken, while doing that inverse, or here itself I will do that, ks I have written here, I will do that here itself. So inversion of this matrix is nothing but ei will go to the top, that is there, here divided by delta is 7 into 4, that is 28 minus 4, that is 24, into this minus 110 minus 20. So this, if you simplify, you will get, this is ks inverse, you will get, I'll tell you the final formula. So ds is given by 1 over ei minus 48 and 4. This is the value you are going to get, d1 and d2. So that is the displacements along coordinates 1 and 2. Then last step, 7th step, to find PM, that is the member yet forces in the element coordinates. So for that we can use this equation. We have PM is nothing but, formula you can remember, PM is nothing but PMF plus Km into dm. This is force in the actual fixed end forces, assuming each is joined to be fixed, and this is the force due to the displacement. And this you can write it as PMF plus Km into dm. By principle of contrariety, it is nothing but R into ds. This ds, just now we have determined, R is known, Km is also known, Pm is also known, so Pm we can determine. So therefore, this Pm is nothing but Pm1, Pm2, Pm3, Pm4. That is the fixed end actions, that is equal to PMF that also you have determined PMS in the first step. You have determined that fixed end actions, that is minus 150 plus 150 minus 40, then 40 plus 40. That is PMF plus Km. Km you have generated, that I have here, that is Km is nothing but you have generated a simple stiffness matrix EI by 6 into this 8 by 6, 4, 8, and 8, 4, 4, 8, 0, 0, then 0, 0, 0, 0, 6, 3, 6, 3. Multiplied by R also we have generated, that is 0, 1, 1, 0, 0, 0, 1, and D you have determined, that is 1 over EI, then minus 48, 4. So if you simplify this, you will get this PM. PM value I have here, straight away right, you will get minus 182, 86, then minus 86, and this 20. So this is final moments here. So that I have written. This completes the analysis of the problem. You have to get in the first step, whatever I have identified, the unknown internal member forces that I have defined here, and that I have calculated here, and in the second step, whatever I have identified as the unknown joint displacement D, that also I have determined in step 6, and with this the analysis is completed, and if you want you can draw the bending moment diagram for this. So straight away that's a very simple process. So this is the beam given ABC, and of course this overhang was there like this. So this was 80 kilonewton, this was 50 kilonewton per meter, this was 10 kilonewton, 2 meters, 2 meters, 2 meters, 6 meters. So now we have determined the fixed end moment here, that is moment here. It is 182 minus means whatever positive side in the direction clockwise I have taken, I have to reverse it. So that's why I am plotting on this right side of the arrow. This is arrow side is right, this is right, always we plot on the right side. That's 182 PM1, and PM2 is positive, that is like this itself, it is 86, it is 182. Here also time is here. So I have to plot it on this side, 86. Then this side it is minus 86, that is like this, minus 86 anti-clockwise, here it is positive, clockwise, here anti-clockwise. So that also I have to plot it on right side, and here I got plus 20 here. Plus 20 means clockwise. Clockwise means arrow is the right side of the arrow is here. This is 20, and here of course it is 0 moment at point B. From this to this I will join, and here I have division, I will get a parabolic thing. So this is a parabolic moment. So here I will get a central triangular moment like this. So that I will superpose on this. So this will be your net bending moment. Of course you can work out these positive moments. You can work out and get the final bending moment diagram for this particular So with this, the analysis of beams is completed. So given beam and same procedure you have to follow. It's a very simple process. All the basic knowledges which I explained well before the lecture, you have to remember that is the relationship between the Km and Ks and also principle of contragradients and element stiffness matrix, all those things you have to remember. Then we can just follow the 7 steps, whatever I have just indicated now to complete the analysis. So next class I will take up one more beam analysis with settlement of support given, and then one problem on truss and one problem on frame by following the same procedure. I may not explain the things now. You are already well versed with the theory. I'll just start working, following these steps, the problem one by one, and we will do that in the next subsequent class.